In the last video, we defined open and closed sets. We proved that they generalize the notion of open and closed intervals, and then we examined some other sets, asking the question open, closed, or neither. Let's continue that conversation. Let's start by proving the claim from the last video, that the only sets that are both open and closed are the empty set and the set of all real numbers. Let's assume that A is a non-empty open set that's also not equal to the reals. We'll then prove that A can't be closed. Let A be an element of A, and B be a real number not in A. Let S be the intersection of the closed interval A to B with the set A. And then let little s be the supremum of S. By the definition of supremum, for any small step down of size epsilon to S minus epsilon, we'll be able to find an element in our set S that's greater than that small step down. So in symbols, we would say that for any epsilon greater than 0, there exists an x in S such that S minus epsilon is less than x is less than or equal to S. And so this x lives in the epsilon neighborhood of S. In other words, we can always find an element of A in the epsilon neighborhood of S. And so S is a limit point of A. And yet, we'll be able to argue that S cannot be contained in A. Assume toward a contradiction that S was an element of A. Then S could not be equal to B, so X would be less than B. By the definition of open, there would exist an epsilon window around S that's entirely contained in A. And we can take the size of that epsilon window to be less than B minus S, so that this epsilon window around S is also contained in our set, big S. But that's a contradiction, because S is supposed to be the supremum, an upper bound for the set, big S. And so big S cannot contain any elements greater than S. So S is not in A. And so we've specifically found a limit point of the set A that's not contained in A. Thus, A is not closed. The reason we needed the assumption that we don't have the empty set and we don't have the set of all real numbers is because we needed both a real number in A and not in A. So we've proven the result that, aside from the empty set and all real numbers, no set can be both open and closed. But there's plenty of sets that are neither. For those sets, we could form their closure or their interior, making them into a closed set or making them into an open set. Given some subset A of the real numbers, let L be the set of all limit points of A. The closure of A is defined to be A union L, and we'll denote it with this A with a bar on top. So, for example, if you took the set of 1 over n, such that n is a natural, this has 0 as its only limit point. So A closure would be A union the set containing 0. And if our set A is, say, an open interval from A to B, then A closure would be the closed interval from A to B. And since every real number can be expressed as the limit of a sequence of rationals, the closure of the rationals equals the reals. In the case where we took the closure of an open interval, the result was clearly a closed set. But it's not immediate that that's always true. So we should state this as a theorem. For any subset A of the reals, the closure of A is a closed set, and furthermore, is the smallest closed set containing A. By definition, we're guaranteed that A closure contains any limit points of A, but maybe we've introduced new limit points of A closure. We need to show that this is not the case. Let's let X sub n be a sequence whose terms are each contained in A closure. And let's suppose that X sub n converges to some X. We need to show that X is an A closure. Let epsilon be greater than 0. By the definition of convergence, there exists a big N in the naturals, such that for all n greater than or equal to big N, the absolute value of xn minus x is less than epsilon over 2. Now let's just fix any index n greater than or equal to big N. Since xn belongs to A closure, xn is either in A or is a limit point of A, meaning for any epsilon window around xn, we can find an element of A contained in that window. And I'll choose the size of that window to be epsilon over 2. stating that there exists some A in A such that the absolute value of A minus xn is less than epsilon over 2. And then by the triangle inequality, the absolute value of A minus x is less than or equal to the absolute value of A minus xn plus the absolute value of xn minus x is less than epsilon over 2 plus epsilon over 2 equals epsilon. So for any epsilon greater than 0, we can find an element of the set A within that epsilon of x, which means that x is a limit point of A. So by definition of A closure, x is an element of A closure. Since A closure contains all of its limit points, it is a closed set. And for the second part of this theorem, we could just note that, say if L represents the set of all limit points of A, then any closed set containing A must also contain L by the definition of closed. So there can't be anything smaller than A union L. For our second main result, let's recall what's meant by the complement of a set in the real numbers. A complement is defined to be all x in the reals, such that x is not in A. A set A is open if and only if A complement is closed. And this would also be equivalent to saying that A is closed if and only if A complement is open, because the complement of A complement is A again. Let's start with the forward direction. Assume A is open. Since we need to show that A complement is closed, let x be a limit point of A complement. So every epsilon neighborhood around x contains some element from A complement, some element not in A. And this means that x can't be an element of A, because by the definition of open, if x was an element of A, that means there would exist some epsilon neighborhood around it that was entirely contained in A. So x is not in A, so x is in A complement, and so A complement is closed. For the reverse direction, let's assume that A complement is closed. Since we need to argue that A is open, let's let x be an arbitrary element of A. Now we need to come up with an epsilon neighborhood around x that's entirely contained in A. Since A complement is closed, x is not a limit point of A complement because it contains all its limit points. So there's some epsilon threshold, there's some epsilon window we could place around x that does not contain any elements from A complement, which means that it would live entirely in A, satisfying the definition for A being open. When we first talked about open sets, we discussed how arbitrary unions of open sets, or finite intersections of open sets, remain open. But we haven't yet had a similar conversations about unions or intersections of closed sets, and it's because I wanted to wait until we had this theorem established to allow us to bootstrap up from what we know about open sets. Let's recall De Morgan's laws from episode 4, describing how unions and intersections interact with complements. And in that context, we just did countable unions and countable intersections, but the same laws and the same reasoning behind the proof hold for uncountable, or we could just say arbitrary unions and intersections. So we could let big lambda be an index set and let A lambda be some set for each lambda in big lambda, and state that the complement of the arbitrary union of all the A lambda is equal to the intersection of the A lambda complement. And on the other hand, the complement of the intersection of the A lambda is equal to the union of the A lambda complement. So these are the most general versions of De Morgan's laws. Let's combine them with the previous theorem to prove results about unions and intersections of closed sets. The union of a finite collection of closed sets is closed. The intersection of an arbitrary collection of closed sets is closed. For the proof of the first part, let's let A1 through AN each be a closed set. Then A1 complement through AN complement are open. And so the intersection of A1 complement through AN complement is open. But that's the same set as the complement of the union of A1 through AN, which means that the union of A1 through AN is closed. And the proof of the second part of this is very similar. To practice combining these closures and complements, let's let A be an open set and B be a closed set. And let's consider various sets and determine whether we can conclusively say if they're open or closed or we're not sure. So what about the set difference, A minus B, which is just all x that are elements of A that aren't elements of B? This is equivalent to the intersection of A and B complement. And A is open and B complement is open. And finite intersections of open sets are open. So this has to be an open set. What about this example? The intersection of the complement of A closure with the closure of A complement. Well, that set on the left is just a subset of that set on the right. Like if X was to live in the complement of A closure, that would mean that X is not in A closure, which would mean X is certainly not in A, which would mean X is in A complement, which would mean X is definitely in A complement closure, a larger set. So this intersection is actually just equal to that set on the left, the complement of A closure. And A closure is a closed set, and so this set is open. What about the set A intersect B, union, A complement intersect B? Instead of intersecting each of these sets with B, we could just first form their union and then intersect that with B. So this set equals A union A complement intersect B, which is just the real numbers, intersect B, which is just B. So it's closed. The closure of a set was a way to add in all the limit points to make it into a closed set. And there's a similar notion for open sets called the interior. We'll define the interior of a set A, denoted like this, to be the set of all X in A, such that there exists an epsilon neighborhood around X contained in A. And just like it wasn't necessarily immediate to show that the closure of a set is actually closed, it's also not immediate that the interior of a set is actually open. Because we not just need that every element has an epsilon neighborhood contained in the original set A, but moreover is contained in the interior of A. Instead of proving that interiors are always open from scratch, we can use the fact that the idea of an interior of a set is very related to the idea of a closure of a set. Let A be a subset of the reals. The interior of A is equal to the complement of the closure of A complement. And there's various ways to write this statement. You could say that the complement of the interior is equal to the closure of the complement, or that the interior of the complement of A is equal to the complement of the closure, or that A closure is equal to the complement of the interior of A complement. These are all just equivalent versions of the same statement. Let's prove the statement as written, showing set inclusion one way and then the other way. We'll start by assuming that we have some element X in the interior of A, and then we'll need to show that X lives in the complement of the closure of A complement. By the definition of interior, there exists epsilon greater than 0, such that the epsilon neighborhood around X is entirely contained in A, which means the intersection of the epsilon neighborhood around X and A complement is the empty set. They share no points in common, and so X is not a limit point of A complement. So X is not in the closure of A complement, so X is in the complement of the closure of A complement. And for the reverse inclusion, let's say that we have an element of X in this other set on the right side, and we'll need to show that it lives in the interior of A. By the definition of complement, X is not an element of the closure of A complement. So X is not a limit point of A complement, which means there exists some epsilon greater than 0 such that the epsilon window around X does not meet A complement. So this specific epsilon window lives entirely in A, which means that X is in the interior of A. And this shows the reverse subset relationship, and so the two sets must be equal. Now the claim that if A is a subset of the real numbers, that the interior of A is an open set, is just a corollary of this previous theorem. Since A complement closure is a closed set, its complement, so A complement closure complement, is an open set, but that's exactly equal to the interior of A, so the interior of A is open. The purpose of the introduction of these dual notions of a closure and an interior is to see how when working with open and closed sets, theorems and definitions can often be expressed in two distinct yet equivalent forms, one from the open perspective and one from the closed perspective. In the next video, we'll discuss compact sets and the Heine-Borel theorem.